Hi everyone. Let's carry on with the next few examples. This is the lesson, I believe it's 8.4. It's area between curves is what we're looking at. And these get into some situations you have not encountered before with integration. So with this example, I want you to notice that this equation is written as an x equals equation. So this is written, we would say, in terms of y. So y is the independent variable here. That's why you have a sideways looking parabola, okay? And so if we were doing this kind of the way we've always done integration, this is what it would look like. By the way, this is not actually what we are going to do because this is way harder. I'm going to show you a different method. But what we would have to do is first we'd have to find where this vertex is, right? So, and I have faith in us. We could do that. We'd have to remember some things from algebra, but we'd have to find where that vertex is. It's not right at 6. And then what we'd have to do is turn this thing into like two separate functions. And that's going to have to do with like the plus or minus that would come out of either quadratic formula or taking a square root. But the positive side of this would be like this top part of the arc, and the negative side would be this bottom part of the arc. So if I could write those two separate equations by doing some crazy solving here, I could do the like one function minus another, right? And so if I did this function minus this function, that would give me this area in between. But I have another option, okay? And this is especially helpful for equations that are written in terms of y. I can integrate along the y-axis instead of integrating along the x-axis. So every integration we've ever done, our endpoints have come off the x-axis. But what I'm going to do this time is I'm going to read this way, okay? So I'm going to integrate from 0 to where this endpoint is. This is right at 5. And by the way I know that is if I were to try to solve this thing, I could factor it, and I would find that 5 is one of my roots. So if you don't believe me, go pull a y out of there. Okay. And then since I'm integrating in terms of y, meaning I'm running along the y-axis, my integral is going to be with a dy on it instead of a dx. Okay. And then I need to make sure my equation matches that. So my equation needs to have y's in it. The good news is this one does. So this is 5y minus y squared dy. But that's just it, right? And when I integrate in terms of y, just like the x-axis integration finds the area between the function and the x-axis, y-axis integration is going to find the area between the function and the y-axis. It's kind of like the graph is sitting this way, right? And we're finding that area underneath the curve. It's just that the underneath looks weird because it's kind of sideways. So I'm not necessarily going to, well, I guess I'm going to have to because I can't turn my camera off there. But I'm just going to head to Desmos to do this. I was going to do that off screen. We have 5y minus y squared. Desmos is totally fine as long as you use a dy here and not a dx. This little button, by the way, will turn your answer back into a fraction. Those are just a little cleaner usually to write down. And so the answer I came out with is 125 over 6. And again, basically what's written right there on my screen is what I would expect to see on your paper as far as work goes. Okay, so let's take a look at example 5 here. Example 5 is harder if you're without a calculator, okay? With a calculator, I think it's not going to be a problem for you, but so it says find the area of this region. And this region here, this is the square root function. And then this is the graph y equals x minus 2. So the problem I'm going to run into with this one, or maybe not a problem, but just something that I want to keep in mind, is when I go to integrate the first function, when I integrate the y equals x squared, that integral is going all the way from 0 to this point, which, by the way, this is at 4 comma 2. We could figure that out by setting these equal to each other and solving or graphing. And like I said, in a minute, I'm going to use Desmos anyway. So if I really needed to, I could pull this up on the graph and take a look at that point. So I would be integrating from 0 to 4. And that would give me all of this area, right? Everything under that square root function. So let me just write that down so we can keep track of what we've done so far. We know we're going to integrate from 0 to 4 of the square root of x function. Okay. The problem is when I go to subtract the other function, I want to get rid of this area here, right? This is what I'm trying to eliminate. But notice that this area, this little triangle, doesn't start at 0. That's because these two graphs don't intersect, right? These are two different endpoints. So for the x minus 2, I'm not integrating all the way from 0 to 4. I'm only integrating from, this is at 2, again, because that would be the x-intercept, right? I'm only integrating from 2 to 4. So this is one that I can't smash together in one integral. I would have to do two separate integrals because their endpoints are different. I'm still subtracting because I am still like when I erased that triangle, that was me subtracting. But this would be from 2 to 4 of the function x minus 2 dx. So I just want you to take a second and, a little Desmos appreciation time, and think about how ugly this would be if we had to do it by hand. Because we would have to do an antiderivative here and plug in two numbers. Antiderivative here, plug in two numbers, and then combine all of that together. Okay? Again, that is not our focus right now. You definitely could be asked to do that by hand, but I am going to trust that you could if you absolutely had to. So we're going to let Desmos do the heavy lifting here. 0 to 4 of square root of x, and then minus integral from 2 to 4 of x minus 2 dx. Final answer there is 10 over 3. But what I want you to think about with this problem is there's actually another way I could approach this. Let's pull that back here. So this next question says, what if we did this in terms of y instead of in terms of x? And I wish I hadn't scribbled quite so much all over my picture, but we'll make this work. If we were standing here on the y-axis and looking upward, or looking outward, I guess, at my graph. So picture it this way. We're standing on our y-axis. Can you see that now I have two very clear start and end points? I'm definitely starting at 0 because all of this is at 0. And I'm ending here at, I didn't trace that line very well, but ending here at 2. So I'm integrating from 0 to 2. The top function would be that linear function, the x minus 2, and the bottom function would be this square root function. So I could integrate everything under the line, which would be all of that. It's like a trapezoid. And then I could erase all of this, everything under the curve. Okay. So integrating with the y-axis is actually simpler because I'm not going to have to do two separate integrals. Sorry, that picture looks really gross right now. So my integral is going to look like this. I know for sure I'm just integrating from 0 to 2 because, again, I'm looking along the y-axis, starting at 0, ending up here at y equals 2. The one thing that we're going to have to do a tiny bit of work for here is our two equations need to be written as x equals equations instead of y equals equations. So just off to the side here, if y equals the square root of x, we want to think about what does that mean x equals. Okay, well, how would you move that to the other side? Well, you'd square the other side. So you would have x equals y squared. If y equals x minus 2, we have to think about what would x equal. That would be x equals y plus 2. If you really wanted to, you could type these graphs into your calculator and see that they look exactly like these two graphs. Okay, this one might give you the full parabola. It might give you the bottom half of this parabola here. But if we're limited to the, the first quadrant, then this is still the shape that I'd be looking at. So, okay. As far as subtraction goes, we said that the line should go first because that would be the top function if I was standing on the y-axis. So y plus 2 minus y squared. We should be fully expecting this answer to come out exactly the same as the answer before because it's still the same shape we're finding the area of. So, integral 0 to 2 And then we said y plus 2 minus y squared dy. And yep, that answer is also 10 over 3. So with a calculator, I mean, either method is probably fine, right? Either one of these methods that's shown on the screen. If you didn't have a calculator and you were doing this by hand, probably this second one would be way easier because you're just dealing with a single antiderivative. And quite honestly, these antiderivatives are probably easier than these ones up here. So just want to show you that you have options for dealing with these questions. Okay, one last one to talk about, and this one I'm primarily going to use Desmos for. Maybe I will try, let's see. I'd really love to have like split screen going on. My laptop screen is just not very large. So, okay, so my two functions this time, well, it's going to go away. I'm going to name them f and g. And g of x was 5 minus x. And then it also mentioned the x-axis, which is the line y equals 0. So sometimes I like to graph that too, because sometimes it's hard to figure out like what area is it that I'm actually talking about here, right? Well, I want to look for an area that's touching all three colors here at the same time, the black, the purple, and the green. And that would be this area that's kind of almost like a triangle, but with the one weird curved side. That's the space I'm trying to find the area of. Okay, so thinking about this in terms of the x-axis, this one's a little bit weird, okay? Because the green and the purple are not stacked on top of each other. This is almost like two separate integrals kind of backed up to each other. So let me show you what I mean by that. See this intersection point right here? Let me pull that point over into our expression list. And then I want to drop a line down right at this x value. So I'm going to say x equals that number. Let me get rid of all the other stuff. Okay. Let's dot that line. Okay. So if I put a line right there, what I want you to be seeing is that this is really an integral under the green function up to that line, right? That serves as like an endpoint for my integral. And then also an integral under the purple function up to that line. And they're kind of just, I keep pointing to the screen, I'm sorry about that, but they're kind of being added together, right? It's this area plus this area this time. So again, well, I've got that number there that I'm going to need. The way I would do this is I would say, I'm going to integrate from 1. If you look at that green graph, it's poking out right there. The starting point is 1. So I'm going from 1 to 3.693. Remember, we want to write down 3 decimal places, even if we're going to use more, of the f of x function. And I probably should in my work clarify which one is f and which one is g. And then I'm going to add an integral starting from that 3.693 up to the endpoint, which I believe is at 5. I'll pull the video, or the camera away in a second so we can see that, of the g of x function. And then again, somewhere here I would say, hey, I'm calling this thing f of x. You'd probably want to be a little more technical if this was like, I don't know, the AP test, but that's g of x. And so I can just type that integral straight in. Integral from 1, if you want to do some copy pasting here with this number, of the f of x function. And then let's add the integral again from that same number up to 5 of the g of x function. Okay, and that's the answer that I come out with, 2.985. But now I want to talk about an alternative, right? There's another way we could have gone about this problem, and either one would be considered correct. Let me just write this answer down. 2.98, I guess I should say 986. Okay. My alternative here would be to think about this in terms of the y-axis. I'm going to take this line off of here. What if I was standing over here on the y-axis and integrating this way, right? If I was doing that, if I was looking at this thing sideways, the purple function would be on top of the green function. So I could, again, just do a single integral. It would be starting at 0 and going up to wherever this intersection point was, but this time it would be a horizontal line. Let me grab that number here. I'm just putting that horizontal line in there for us. Okay. So I would integrate from 0 to here, the purple function minus the green function. And again, if we were in class, I'd be taking my computer and like turning it sideways so you can see the purple function on top of the green. What we are going to have to do with that is, in order to do it in terms of y, we need to write our equations in terms of y. So again, if I have f of x equals, or I guess I can just say y equals natural log of x, how do we get x alone? Okay, hopefully you've gotten really good at this. Y equals natural log of x, that's the same thing as saying x equals e to the power of y. Remember, e's and natural logs undo each other. If I have y equals 5 minus x, whoops, not an equals. I'm kind of thinking about this as like adding the x to the left and then subtracting the y from the right. So I end up with this, x equals 5 minus y. And so my integral setup this time would be, we're going to integrate. This is in terms of y. Sometimes I like to write that down first so I remember that that's what I'm doing. Along the y-axis, I'm going from bottom to top. So the lowest value there is 0. And the highest value is that 1.307 number that I see on the screen there. And I'm going to do the 5 minus y, because that's the farthest one away, minus e to the y. Oh, pen's dying just in time. Okay, let's see what we get, because we should get this same answer, right? We should get this same 2.985. This is getting real low down on the screen here. Bring that up a little. So we want to integrate. Oh, I wanted that number. Shouldn't have done that. There we go. I wanted to copy that. Okay. Integrate from 0 up to that magic number of the function 5 minus y minus e to the y dy. And you'll notice you get the exact same answer. Decimals are a little off because of the rounding of those endpoints. Okay, if you had rounded those endpoints further, you'd probably be further off. But as long as you're correct to 3 decimal places, which if you look, these are the same for 3 decimal places and a little bit beyond, we should be good to go. So 2.986 would be my answer there as well. Okay, so that gave you an idea of just a couple of the strategies that you can use. I would really recommend against trying to memorize this as a formula. So let me show you what I mean by that. Back on this first page, this little thing in the box that I gave you where it says area between 2 curves. This is sort of a general strategy, but I would not think of it as a formula, because there's a lot of formulas in this unit that are going to look really similar to this one. And if you try to just memorize them, first of all, it's going to be hard to memorize. There's a high likelihood that you'll screw it up. Okay, not you personally, but just anybody trying to memorize them, because they all look the same. The second thing is, there's a lot of situations, you've seen some here, where we can't just apply a formula directly. We really have to think through like what is happening and what are we allowed to do and things like that. So you're much better off understanding why you're doing what you're doing than just blankly memorizing this formula. Okay, so again, think of that as a strategy, but not necessarily a blueprint to get you all the way to your answer. Okay, that's it for this lesson. More to come on this. We're going to be spending lots of time doing these types of areas, so you'll get lots of practice with this. But if you do have questions, I will see you in class.